I'm Wei Zhou from Huazhou University of Science and Technology. It is a great honor today to present our study about MPU usage. This is my agenda. I will first give some basic background about MPU and its adoptions in the popular OS, and then we will focus on some common pitfalls and limitations in the MPU usage. And I will also give some mitigation suggestions to these issues, and finally I will summarize our work. I think everyone here is familiar with the MMU, which has been widely used in our modern systems. However, MMU is absent in the resource-constrained microcontrollers, and as a replacement, ARM has been proposed MPU as a stripped-down MMU to protect their systems. So at first, what is MPU? The function of MPU seems similar with MMU. MPU can send different permissions to different memory range based on current privilege level, and if the permission is valid, a fault handler will be raised, and it can only be configured by the privilege code. And so how to use MPU? Developers only need to configure the MPU register. For example, the control register is used to enable the MPU, and the region address register is used to configure the start and the address of each memory range. The range register is used to configure the access permissions, including read, write, and executable for the different memory range. And however, to know that, the MPU imposes the rejections constraints on the range configurations. First, the range at least the 32 bytes, and the size must be aligned with the power of 2. And the biggest constraint on MPU is the range number, up to 8 for the most ARM Cortex M series. And in the last ARM8 Arch, the program model become a bit more flexible. MPU on ARMv8 could use separate start and limited address an address register to define the attributes address space for memory range, and also introduce a new attribute register to share the same memory attributes with different memory with different access permissions. But although the number of MPU range is still limited, but it has been increased to the 16. So it seems MPU should be very useful. So we are curious about whether the MPU has been widely adopted in our real-world embedded systems, and what security functions have been provided with MPU. Therefore, we did a comprehensive study on the MPU usage of a top IoT operating system in the market. First, we found the following security functions has been supported. First, code ranges can be set as non-readable to achieve code integrity check, and the no acceptable for the data range like the DEP can provide, and also can achieve start guard with a small inaccessible memory range after the start boundary, and RTOS will also can take advantage of MPU to achieve the user and kernel space separations like the Linux kernel, and I will detail this feature later with concrete examples. However, as a result, you can see the table. To our surprise, only a few MPU OS use MPU, especially for the open source. Even if the MPU is supported by all these devices, and only a few security features are also enabled by default. In this work, we are trying to find why MPU has been outcast in our real world. So this is our research questions. We are trying to answer why the MPU have been not widely used in operating system in the real world, and why do only a few OS able the full blow-down MPU-able protections by default, and how do this OS implemented the MPU-enabled protections? And MPU-enabled protections is really effective. So let's look two case studies of MPU usage at first. In detail, for the OS does not use the MPU for the kernel and the user space privilege separations. It will always run all code under the privilege level. So only the basic MPU security features they can adopt. For example, here RIoT sets a whole range as a no accessible to achieve the DEP, and it also define a minimum MPU range at the boundary of the main stack and the user stack to define the stack overflow. And here in combinations, the FreeRTOS MPU not only enable the DEP and the CIP, but also use the MPU to achieve the user and the kernel separations with 5 MPU ranges. And fourth, like RIoT, it assigns range 0 as a non-readable to achieve the integrity, and the data range of the kernel stack and the peripherals as no accessible to achieve the DEP. And furthermore, the FreeRTOS dynamic switch changes the range for the different user stacks switch. So to keep each user stack can only access their own stack, and all the kernel code and the data can only be accessed with the privilege level. Yes, so the user stack cannot access these ranges. And due to the time limit, the detailed MPU usage of other OS can be found in our paper. And next, I will focus on the common limitations and pitfalls in MPU usage to answer our research questions. We summarize the common pitfalls on the file access. First, I show how to disable or we can easily bypass the protections provided by MPU with this real-world OS. First, let's see the RIoT OS. As I mentioned before, since the MPU register can be configured by the privilege code, and RIoT also provides the developer right to use the driver API for the MPU configurations. So if any buffer could be overflow in the firmware, the attacker can use it to call the MPU disable function in the kernel. Yes, so it can shut down all MPU functions to disable the protections. And for the FreeRTOS MPU version, it seems more security. However, due to the user and kernel space separations has been enforced. So if an unprivileged task wants to use the kernel functions, it must go through the system call. However, we found FreeRTOS does not provide a new kernel API for system call, just wipe the original kernel API with a privilege switch functions with a SVC interrupt. For example, here, if an unprivileged wants to use the kernel functions, like the MPU delay, it will call the MPU wipe function to raise the privilege. And then it will call the kernel function. And when the kernel function completes, it will reset the privilege function and call and to drop the privilege. So we found the bug here. Then the system call code range is available to the user model task. So when the MPU privilege switch functions is also inside the system call, exposed to the unprivileged task. So as the unprivileged task can directly call this privilege raise function to raise the privilege. And to fix these issues, FreeRTOS has replaced the privilege raise function as a macro, so it cannot be directly called this raise privilege individually. But this really solved the problems. And when we look deeper with this web functions with binary code, we can find the system call will first store the original caller privilege level in the stack, and then it will use the interrupt to raise the privilege and to call the kernel functions, and finally it will withdraw the privilege level. on the stack and to check whether the caller is unprivileged. And it will does, then it will reset the privilege level. However, if the unprivileged task has been compromised, and it will can directly call the SVC instruction, it's a SVC interrupt inside the system call. And then further it can manipulate the privilege level in the unprivileged stack. So when the kernel function is finished, it will not drop the back to the privilege level, but directly return the kernel function, the system call function. So let me further to detail the explosion step with a simple demo. Both the attacker can overflow any buffer on unprivileged task and replace the function return address as the SVC instructions in the system call. For example, here we use the MPU task delay for this example. And when the function return, it will jump to the SVC instructions, and then next it will call the kernel function. And here when it finish the kernel functions, it will read the original privilege level from the user mode stack. Here, so we can further manipulate the stack data to fix the privilege level on stack as the privilege level. So when the firmware withdraws the privilege level from the stack, it will mistake the original kernel, it will take the miss privilege level and think the original caller is privileged. So it will directly return with alt to resetting the privilege. This bug has also been patched by FreeRTOS, and it changes the privilege level check at the beginning of the system call. So if even if the attacker now jump into the SVC instruction in the middle of the system call, it will force to reset the privilege. And now I will discuss some other pitfalls of the MPU usage. And we further found that even if the implementation has no flaw, the protection provided by MPU is still limited. For example, it cannot protect the interrupts, since all interrupter address tables cannot be monitored by MPU, and the interrupt always run under the privilege level, and the developer cannot assign specific interrupter handlers as unprivileged for some user tasks. And also due to the range constraint, MPU is not also suitable for protecting the peripherals with a very small range. Also, the advanced protections as the no escapable only protections cannot achieved by the MPU. And privilege permissions always beyond the unprivileged. So it cannot use to protect the security applications when the OS has been compromised. And also the MPU also do not restrict the peripheral as master, allowing them to access all memories like the DMA. And also we found to limit MPU to realize the user and task separations, invoke the kernel API must go through to call the system call, and for the privilege switch, this will also incur too much delay when tasks need to call many kernel functions. Consider more applications in our become more competitive. It will cause the deadline constraints. So the overhead cannot be ignored. And also the MPU range for the different user tasks, as I just demonstrated before, is needed to be updated during the task switch. It also will incur the time delay. And we also found that the memory range number constraint is a main problem for the real-world OS usage. For example, it's very few available user-defined additional ranges for the privileged solutions. It will consume many ranges to protect the different individual peripherals. And we also found no OS to protect the shared memory protections by default. It will use too many ranges. And interestingly, we also found we cannot enable too many security features at the same time with MPU. For example, if we enable all the MPU features provided by Tizen OS, it will become no more any available MPU ranges for the user applications. And porting the software language MPU will also cause compatibility issues. We have witnessed many of them on the developer forum. And also the chip manufacturers may design custom MPUs to protect the better security performance. For example, we found the NSP MPU to replace the ARM MPU. It can reject the permissions of the peripheral as a master. When enabled by default, the peripheral cannot access the memory. However, to use it, the developer has to properly configure the MPU. Otherwise, many official demos cannot become executed. So I will give some suggestions to minimum the pitfalls. First, to be careful about the privilege overlap. Since the ARM allows MPU ranges to overlap, that means the higher number ranges always have priority. So we recommend for the system protection ranges should use the higher numbers, and let the user define the application MPU range number as a lower. Second, as I demonstrated before, to be careful about the privilege risk issues for inside the system core. Ideally, I recommend to the MPU or MCU OS should use the individual system core like the kernels for the kernel API with the software interrupt like the modern systems like the kernels and not just a web of them. If web of them, you should perform additional checks for the caller and to make sure the caller is privileged. If it is unprivileged, it must be dropped down after the system call. And even some RTOS do not use the privilege separations for the kernel and the task. It only enables the general protections like IoT. However, in case the attacker can bypass the MPU protections, we recommend the system should drop the privilege after any MPU configurations. And also, as I demonstrated before, the number of ranges is very limited in the ARM series. So I also give some suggestions to minimum the memory number use. First, the developer should beware of the default address map permissions. ARM defines the default memory access permissions, which are directly enforced by CPU, no need for the MPU. For example, the peripheral range is not accessible by default, so it's no need to waste another MPU region to assign no accessible for the peripherals. And we also found no MPU have been used, no OS have been used MPU sub-range features, which can divide one MPU ranges into 8 equal size sub-range and could enable of them individually. For example, if there are two tasks, task A needs 5 KB for its start, and task B needs 3 KB for its start. So, without the sub-range feature, due to the alignment constraint, the OS will assign 8 KB for task B and 4 KB for task A. So it will be the 12 KB memory consumption. And if we use the sub-ranges, we can only need one MPU ranges with 8 KB and enable the higher 5 KB when task B is running, and enable the lower KB 3 KB for the sub-range for the task A is running. And also, as a supplement, we can also learn how to use MPU range for the academic committee. For example, the minimum proposed to isolate the stack with the memory wheel switch. It protects the task and the kernel are all running with the unprivileged level to reduce the overhead incurred by the privileged switch to call the kernel APIs. And we can also take advantage more hardware features to achieve more system protections, like the ARM-based arch, also to provide trust zone technologies. We can also use the screen range of the trust zone as additional ranges and to protect some more memories. And also the trust light can also propose a new MPU design, which are not only to check the data access, but additional consider the current MPC as the subject to perform the access. To quickly summarize our work, we found MPU as a ready-to-use features to protect the MCU, but is rarely used in the real-world OS. And after we study this OS, we can find some common pitfalls, and some flaws are fundamentals and cannot be easily to remove in a short term. So we also give some recommendations for better use of the MPU. And all bugs I just dumped before has been patched in the FreeRTOS kernels. And for the RIoT, since they don't use the MPU to the user space and the kernel space separations, it seems it just increase a very small attacker surface for their products. And this is all my talk. Thanks for listening, and I'm happy to take any questions.
Hi, this is Derek McKee from MIT Lincoln Laboratory. I see that you cited ACEs as related work. Can you compare your work with ACEs?
ACEs is use the MPU ranges for to protect the RP attack. My work is not to design a new MPU design or not use not to teach how to not implement the best the MPU usage. We just shine light down the common limitation and pitfalls of the MPU usage. And if you use the ACEs, you can maybe achieve the more secure feature to defend the RP attack, but it also limited the range numbers. So if the protection is still limited due to the fundamental of the MPU design.